Hi guys, good evening.
Good evening, sir.
Good evening.
Good evening. Okay, let me share my screen. Okay, fine. So let's get started. Uh, so, all right. So today we are going to look at the gradient-based methods. Um, so we're going to look at the gradient methods. For the solution of linear systems. Okay, so that is what we'll look at. So essentially, these are a class of methods. So one thing is, of course, what we learned in the last class was the Jacobi method and the Gauss-Seidel method. Although the Gauss-Seidel method is much faster, even the Gauss-Seidel successive over relaxation. So although GSSOR is much faster than the Jacobi and Gauss-Seidel, all of them in general, actually, for all practical problems, they are still, kind of slow to converge. Okay, so as a result, you will not see them directly being used in solving, big systems. Rather, a variant of this, which is known as a multigrid method, is kind of popularly used, within which it's going to make use of your Gauss-Seidel or Gauss-Seidel SOR and so on. Okay, so but we're not going to look at the multigrid method because that itself will take. I mean, it's not there in the syllabus, and that itself will take 3-4 lectures to kind of completely look at it. But then, nonetheless, these form the basis for iterative methods. Okay. Now, another popular set of methods which are actually fast at convergence compared to these Gauss-Seidel or Jacobi or the successive or relaxation methods are the gradient methods. Okay, which we want to understand today. And these gradient methods were so the gradient methods were originally developed. So essentially, these were developed for solving A times X equal to B or A times B equal to B when the matrix A is symmetric and positive definite. Okay. That means we want symmetric and positive definite. Okay. So what is a symmetric and a positive definite matrix? We know that symmetric matrix is something which is whose transpose is the same as itself, right? If you're going to transpose a matrix, if it comes out to be exactly same as the original matrix, then it is known as a symmetric matrix. Okay, and so that is the first point. And what is a positive definite matrix? Positive definite matrix is one. If you were to take any vector, let us say phi transpose A phi is greater than 0 for all phi not equal to 0. That means if I'm going to take any vector, either phi or x or something, so phi is a vector of values. It could contain positive values, negative values, and so on. But then when you multiply, when you take product of phi transpose times the matrix times phi is greater than 0, for all values of phi that is other than 0, then if this is greater than 0, then we call that the matrix A is a positive definite, okay, matrix. So this has certain implications, and depending on the boundary conditions we get, the matrices that we kind of work with are actually positive definite and sometimes symmetric. So for all these matrices that belong to this class of symmetric positive definite matrices, we can apply these gradient methods that we're going to discuss. Okay, so there are two gradient methods. One is known as the steepest descent method. The other one is known as the conjugate gradient method. Okay, steepest descent method is what we're going to look at today. And then depending on the time and interest, we'll look at conjugate related method sometime next week. Okay, fine. So what does these gradient methods do? The gradient methods actually they're kind of very interesting because if we wish to solve for ax equal to b or a phi equal to b, till now we have learned how to solve for ax equal to b by applying operations on the matrix A. Either we were doing Gaussian elimination or we were doing LU decomposition on things like that, or we have identified certain pattern. We said this is basically tridiagonal matrix, or it is a tridiagonal block, tridiagonal matrix, and so on, right? So with all the structure of A, we were trying to solve for phi, right? So we were trying to solve for phi for a given right-hand side. That's what we were doing, okay? But then the gradient methods actually, what they do is that they do not solve for a phi equal to b, right? A phi equal to b is actually a linear problem, right? Because this is a linear system, okay? The gradient methods do not solve for this particular problem, the linear problem. They actually solve for a non-linear problem, okay? Non-linear problem, which is a modified version of a phi equal to b. Okay, now it may sound little unintuitive because it appears as if we are going to actually make it more complicated. When we are given a linear problem, why are we actually looking at a non-linear problem, right? That is more complicated, but it turns out it is not so. They construct another non-linear problem from a phi equal to b. So they construct something known as a function, okay? A function q, which is a function of phi, okay? Now here, although I am not explicitly writing anything here, you all realize that phi is actually a vector, right? When we write a phi equal to b, we know that phi is a vector, b is a vector, and then a is a matrix, right? If I were to denote it using 1 over bar for vectors and 2 over bar for a matrix, we know that this is actually a vector, and a is a matrix. Similarly, p is a vector, and q is actually a function of vector quantities. Okay, so q is a function of vector quantities. Okay, so we are constructing, that means q is also a vector, right? Q is also a vector which is a function of vectors. Okay, so but I will not use the over bars, but from now on we realize that whenever I write q of phi, we are actually talking about well, q need not q. Okay, so whenever I say q of phi, we know that we're going to talk about a a vector quantity as such. Okay, so the q need not be vector. Okay, I can actually look at function of vectors. Okay, so this is q of phi, but we know that phi is a vector quantity. Okay, so the value that it's going to construct, which is q of phi, is going to be half of p transpose a phi minus b transpose phi plus c. Okay, so this is the quantity that this particular gradient methods use. Okay, they construct a non-linear thing. As you can see, there is phi transpose a phi. This is basically non-linear because you have phi being multiplied with phi itself. So this is a non-linear function that they have constructed. Now, what they hypothesize or what they kind of say is that the minimum. So if we can minimize this function q, so if we can minimize the function q of phi, then that minimization problem, the solution for that minimization problem, the solution for the minimization problem, that is, you're going to get some phi where q of phi is minimum. Okay, that is the same as solving for a phi equal to b. That means that is going to be the same phi as we wanted to obtain from a phi equal to b. Okay, so that is the idea. Now, okay, this looks quite interesting because we were asked to calculate what is a phi equal to b, calculate phi, but we are saying I'm constructing a function q which is a function of phi, vector of phi, and then it is equal to half of phi transpose a phi minus b transpose phi plus c, and then this is going to be if I can calculate the minimization problem of this function, then I know that the phi value where it is going to be minimum is actually the solution phi, and that is going to be same as phi equal to A inverse B, okay, which we are trying to looking for, okay. So that is kind of a quite interesting thing. So I'm going to now kind of prove that this minimization problem is actually same as solving for A phi equal to B when we have symmetric and positive definite matrices, okay. And then once we prove that, we're going to see how steepest descent method is going to work. Okay, fine. So all right, so then let us look at Q of phi. So Q of phi is already given, which is half of phi transpose A phi minus B transpose phi plus C. Okay. Now, if I'm given a function, what would be its gradient denote as? What would its gradient denote? Right? That means if I were to calculate what is Q prime of P, what does it denote? This basically denotes the direction, right, in which Q, right? So Q of Phi basically tells you the direction in which Q changes or Q in which Q increases the most, right? So that is what Q of phi actually represents. So Q of phi, the derivative of phi or the gradient of phi, is actually telling you that the corresponding ijk, if you were to write, and these quantities, when you put it if you want to plot them, then it basically denotes the direction. These vectors, the gradient of phi, are going to point to a direction where, or point to a direction in which this phi is going to increase the maximum, okay, where there is a maximum possible increase for phi at that particular location Q, okay, at that particular location phi, okay, at that particular location phi, what is the maximum increase or the maximum increase direction for Q, right? So that is what Q of phi actually denotes. Okay, so maybe to get an idea, let me draw something here. Let us say we have some function, okay. So I'm plotting some Q of phi. Let us say Q of phi is some function like this, okay. So this is some kind of a surface I have drawn, okay. This surface is basically something like this, okay. So this is a surface. Okay, so I have a surface like this. So this is the surface, and so the surface is, as you can see, this is so this is surface, okay. So this is surface. So using the surface, I want to, so this is surface Q, or sorry, not phi Q. And if I were to plot this surface as levels or contours, that means if I'm going to, take some, cut it with certain values of Q, like, I want to cut it with 1 value, 2 values, 3 values, and so on. So I'm passing several values of Q, and then if I were to plot all these values, let us say the contours which are corresponding to these surfaces, which are corresponding to different values of Q equals 1, 2, 3, some values, okay, 10, 50, something like that. They will come out to be something like this, okay. So the contours are going to look like, let us say they look like this, okay. These are the contours, okay. These are the isosurface contours of Q. That means this, on this entire surface, Q equals some value, okay. So Q equals, let us say Q equals 15, Q equals 10, Q equals 5, and so on. So these are the contours which basically are obtained by cutting this thing, okay. So essentially, this is a 3D picture. This is a 2D picture, okay. These are the contours of phi. Now, what does the gradient of phi denote? Gradient of phi actually denotes, as I said, what is the maximum, what is the direction in which it is changing the maximum. That means if I'm going to calculate what is gradient of phi at this point, it's going to show it this way, right? Similarly, if I calculate it here, it's going to show this way, because these are the directions in which it is changing the maximum, okay? So the gradient at this point will be like this, and this like this, and so on. So essentially, it's telling you that if you go radially out approximately, then that is the direction in which there is a maximum change. That means your Q is going from, let us say, 1, 2, 3, 5, 10, 15. So it is actually changing the maximum in this direction. Okay. So these are your derivative, right? Derivative values, or in general, this is the direction in which the gradient is there, right? Essentially, when you talk about grad of Q, or essentially partial of any this thing of Q, right? So that is the direction. So essentially, we are saying that the gradient is the direction which is the maximum increase in the value of Q at that particular point phi. Okay, if that is clear, then let me try to calculate what is derivative of Q. Okay, that means because Q is given as Q of phi equals half of phi transpose A phi minus B transpose phi plus C, the Q of phi, the derivative of Q of phi is going to be, okay, I'm doing actually some, I'm skipping several steps here. I'm going to write this, I know, essentially from linear algebra. So this is going to be half of A transpose phi plus half of A times phi minus B transpose. We know that the derivative of C with respect to phi is going to be 0, right? I mean, what did I do here? I mean, when I write Q prime of phi, I calculated what is dQ by d phi, right? That is what I have calculated. Okay, so so what is this quantity? So this quantity is okay. So you can think of phi transpose phi times A as something like, if phi were x, this was something like ax square. If it were scalars, we would have written ax square. But then because these are vectors, we have written as phi transpose A phi. So ax square. Okay. What would be the derivative of ax square with respect to x? It's going to be half time ax. Okay. So you're going to get the same thing. Sorry, half times ax times 2, right? 2ax. So you're going to get basically ax. But then when you have matrices, when you want to take derivative of matrix with respect to a vector, okay, you will actually get, you take derivative with respect to phi transpose, then you take derivative with respect to phi. That is going to give you two matrices, essentially half of A transpose phi and half of A phi. Okay, so that is the two values that you got here. And then B transpose phi is more like your B times X. So B times X derivative would be B. Okay, so basically we got minus B transpose. Okay. Or I can even write, actually this is going to be just B, right? Because it's just a vector, column vector, so the transpose disappears. Okay, so this you can obtain after some linear algebra manipulations, which I'm not kind of telling you here. So we obtained this thing, which is the derivative now. But then we said that the matrix needs to be a symmetric matrix. So we have, for a symmetric matrix, A transpose equals A. Okay, that means this quantity A transpose is equal to A. That means I can write the first quantity also as half of A phi. The second one is also half of A phi minus B, which is basically two halves add up, and then we have A phi minus B. Okay, so that is the derivative of Q of P equals A phi minus B. Okay, so that is something we keep in mind for now. Okay, that's the result we keep in mind. Q of P, which is the gradient, right, is nothing but A phi minus B. Okay, I think it looks like now we are on the track of what we want to solve. We said that if you have a minimization problem, right, we know that we basically take a derivative of with respect to phi of something and set it equal to 0. So I have already taken derivative. I just have to set this equal to 0. So if I set it equal to 0, I am actually solving for A phi equals B. Okay, which is what I want to solve. I want to obtain what is phi, and then instead of solving A phi equal to B directly, if I were to just minimize this problem, this nonlinear problem, that is going to give me what is the value of phi. Okay, so that is the idea of these gradient methods. Okay, so now we have used the fact that this is actually a symmetric matrix. Okay, but then what is the guarantee that there exists a minimum? Okay, that there exists a minimum and it is unique, right? And that means there exists a global minimum and it is unique, right? For this, we kind of look at, let me define what is error at any iteration equals phi n minus phi, okay? Where phi is the solution at any step n and phi is the exact solution. Okay, and E is the error vector. Okay, that is the error vector. Okay, then I can write what is Q of Pn equals same as what I have written before. This is going to be phi n transpose A phi n minus B transpose Pn plus C. Okay. Let me look at what is substitute for what is phi n from here. So phi n is going to be capital Phi plus E. So Q of P plus E is going to be half of, okay, this is going to be phi plus E transpose A times P plus E minus B transpose phi plus E plus C. Okay, that's what I have. So if I were to expand this thing, that is Q of P plus E equals half of phi transpose A phi. So that is what I get from the first terms. Then I get half of phi transpose AE plus half of E transpose A phi plus half of E transpose AE minus B transpose phi minus B transpose E plus C. Okay. So I obtained all this thing, but then I want to kind of club these things. Phi transpose A phi minus B transpose phi plus C. Okay, let me write all these things together. So this is going to be half of P transpose A phi minus B transpose phi plus C. Okay, plus I have these quantities, these two quantities, which are half of phi transpose A times E plus half of E transpose A times phi, plus I have half of E transpose AE minus B transpose E, right? That is what is remaining. This B transpose E and these were remaining. That's what I have written towards the end. Okay. What is this quantity? This quantity is nothing but Q of phi, right? Because I have written half of phi transpose A phi minus B transpose phi plus C. This is Q of phi plus what is phi transpose times A? Phi transpose times A is nothing but A phi, right? But then A phi equal to B, but B transpose times A would be B transpose. Similarly, A times phi equal to B, right? A phi equal to B. Phi is the exact solution here. So what I have is half of B transpose E plus half of E transpose B. This is nothing but two halves of B transpose E and E transpose B. B and E are two vectors. If you take transpose of the one and then multiply, they are going to basically give you an inner product. So that means two halves become one. I can write this as B transpose E or E transpose B. And then I add the remaining terms here, which is half of E transpose AE minus B transpose E. Okay, but then we realize that there is a minus B transpose E and plus B transpose E here, so I can strike them off. So I am basically ending up with two terms, Q of phi plus E equals Q of phi plus half of E transpose AE. Okay, now this is the main result, okay, for proving that it is actually should be symmetric positive definite. It should be positive definite. Okay, so what does this mean? This means that Q of phi is our exact solution. Q of phi plus E is solution with some error. We have some error, but then it is always, so if my matrix A is positive definite, then this quantity is always greater than 0. That means irrespective of whether my E is greater than 0 or less than 0, this quantity is always positive, which tells me that Q of P plus E, when I have any error in the solution, that is always greater than Q of phi. Okay, that means that when and this will only happen when there is a minimum, right? Only when there is a minimum and that minimum error equal to 0, only then we're going to get Q of phi as the minimum value, right? Because otherwise everything else will be higher than the exact solution by this much amount, right? Everything else will be higher than the Q of phi, which is the exact solution, by this much amount, which tells you that all other values are actually higher than this thing. That means there is a minimum at E equal to 0, right? And that is only possible when you have a positive definite matrix. So I have half of E transpose AE is always positive. Okay. So, and we also know that for a positive definite matrix, it has all positive eigenvalues, which indicates that, which basically guarantees that there exists a global minimum. okay, for this function. Okay, so with these two things, we now consider that solving for q of phi equal to 0, or minimization of q of phi, okay, minimization of q of phi is the same as solving for a phi equal to b, provided A is symmetric and a positive definite matrix. Okay, so that is the takeaway. Fine. So, okay, now we have done almost 25 minutes of discussion, but all this is related for, in general, for gradient methods. Okay, so now we're going to call upon a particular method, that is the steepest descent method. That is the steepest descent method. Okay, all right. So let us say if you have q of phi, but then phi is a let us say this is a one-dimensional quantity. Okay, this is a one-dimensional vector. Okay, then q of phi. Let us say if I have phi as a, maybe instead of a one-dimensional vector, let us say phi is a scalar. Okay, phi is a scalar. Okay, it is not even a vector. Let us say if phi is a scalar, q is just a function of a scalar. That means this is more like y of x. Okay, if this is the case, then if I consider, let us say, my phi of x as, because it's a scalar, it basically comes out to be some kind of a parabola. So let us say the parabola is like this. So then we know that there is so this is my function q of phi, for phi being a scalar. Okay, because what I have is basically half of phi transpose a phi. It basically comes out to be ax square, something like this, ax square minus bx plus c. That's all, right? So my matrix has become just singular, one, right? Because I'm trying to solve for what is the this point. That's all. Okay, so how do I get to this point? I can get to this point if I'm anywhere on anywhere here. So the fastest way I can get to this point, which is basically my solution, which is phi, which is going to give me a phi equal to b, is by taking, if I start anywhere, I would take, basically I would descend in the fastest possible way in several steps, and then I arrive at the minimum point, right? If I can do that, that is the fastest way I can arrive at this point. And that is what we do in the steepest descent method. So at every location, we're going to identify if I'm going to slide down in which of these directions, so that I can reach the minimum point quickly. So we're going to find for any given point what is the direction in which I can slide down, which is basically going to be the highest decrease in the value of phi, in the value of q. And then we're going to take that direction and then slide down by certain value. Then we're going to stop and then again look at what is the, from this point, what is the direction which I should slide down, such that I reach, such that q decreases by the maximum. Okay, so that is what we're going to do. We're going to take steps in the steepest possible directions, and we're going to descend or slide down this curve and then reach the minimum point. So once we reach the minimum point, we know what is that phi there is actually the solution for a phi equal to b. Okay, so far so good. So this is nice when we try to do it in one dimensions. But then when you actually solve for phi as a vector, right, then what happens is that this q of phi will not be a simple parabola, but it will be an n-dimensional paraboloid. Okay, this is an n-dimensional paraboloid in that case. But in that case also, we can identify what is the steepest descent, DES CENT, steepest descent direction. Okay, that means maximum decrease direction. What is the direction? And if in that direction I'm going to take some step and then stop at some point and then look at what is the next maximum decrease direction and then go down in that direction for a certain distance and so on. Okay, so that is what we're doing. But then we said that q prime of phi, which is equal to, we obtained it as a phi minus b, right? That's what we have obtained before. We said this is direction is actually the maximum increase direction, right? This is the direction which increases maximum. Then what would be a possible direction for maximum decrease, right? So that decrease is basically going to be, if something is increasing in this direction maximum possible, it must decrease. If you go in the opposite direction, it's going to decrease, right? That means minus q prime phi would be the maximum decrease direction, right? It should be opposite to the way it is increasing. So we go, if it says it's increasing highly in this direction, we take the opposite route. So we are basically going to decrease, right? So minus q prime phi, which is going to be equal to minus of this quantity, that is b minus a phi, would be the direction in which we want to go, right? That is going to be the direction which we want to take. Okay. Then let me kind of define a couple of things. What is error? En equals phi n minus phi. Again, phi is the exact solution. Phi n is the solution at time level n. Okay, and en is the error. Okay, en is the error. Okay, so we have all this. Then let me also calculate what is Rn. Rn is basically the residual that we have. What is residual? Residual means the amount by which or the difference in, or the difference between a phi and b, or b and a phi. Okay, that means Rn is going to be b minus a phi n. Okay, that means you have calculated, you found some phi, but then when you actually multiply a with that phi, it's not going to give you b. There is some difference. That means phi is not correct solution. So that difference is going to be residual. That means what does residual mean? That means if you have a system a phi equal to b, take everything to one side. For example, I take a phi to right hand side. So b minus a phi would be, if it were equal to 0, then phi is my correct solution. When this is not equal to 0, then phi is not the correct solution, and that amount by which it is not equal to 0 is nothing but the residual. So if you work with any software, you will see that it basically plots residuals as a function of iteration or as a function of time. So what is it saying? It's plotting these residuals, and we see that, oh, the residuals are decreasing with respect to iterations. That means what is happening is that it is solving, it is, the solution you're getting phi is actually approximating a times phi better and better. That means you're getting to the correct b, okay, because phi is getting better and better, so that a phi equal to p. Okay, so that is why residuals are decreasing when you use some software. Okay, so this is b minus a phi n. That means I can also write b minus a times phi n. I can substitute for phi n from here as phi plus e. Okay, so this is going to be b minus a phi minus a e n. Okay, but because phi is the exact solution, b minus a phi is equal to 0 minus a e n. That means my residual Rn is equal to minus a e n. Okay, that means it is the product of the matrix A times the error at that particular iteration. That is my residual. But my residual is also equal to b minus a phi n. But what is b minus a phi n? We just defined b minus a phi n is the steepest descent direction, right? This is the steepest descent direction. That means if I calculate residual at any iteration, that itself tells me that I should go in the direction of the residual, right? Because that is b minus a phi n, which is the derivative of q prime, right? Minus q prime, or derivative of q prime with a minus sign, right? That means my residual at any particular iteration is going to tell me that, oh, I should go in the direction of residual. That is going to be my steepest decrease direction. Okay, so okay, we have established that residual is the same as the steepest descent direction, and steepest descent direction is equal to b minus a phi. Okay, so these two we have established. All right. Okay. Now let me consider this quantity, that is q of phi n plus 1 equal to So we already obtained this relation. Q of phi n plus 1 is half of phi transpose A phi. Okay, I'm writing the same expression, but with n plus 1 as the iteration count. So we should not get confused that this n plus 1 is actually exponent. It is just indicating that the value of phi at n plus 1th iteration minus B transpose phi n plus 1 plus C. Okay, so this is what we have. Now, if I want to calculate maximum or minimum, I have to differentiate this with respect to P, right? I have to differentiate this with respect to P. Okay. Before that, let me say that, so we are going to take, let us say we want to obtain what is phi n plus 1. We want to take several steps phi n plus alpha n times delta phi n. Okay, so we want to come up with or use something like this. So this is our existing solution. We want to improve the existing solution and call that as phi n plus 1. But then how do we improve the existing solution? We want to take certain direction. We want to take a step of certain length. So we want to take a step of alpha n. Okay, so these are all, when I say n, these are all actually nth time level. And we want to go in a particular direction. So in one particular direction, I want to take a certain length and then go down the sliding in the n-dimensional paraboloid, and then add that to the phi n that I was originally at. And then I keep doing this thing. But then, of course, my alpha is now not known because I don't know how much step I should go down. And at the same time, I don't know the direction, in which direction should I actually go. But then we have now just established that the direction is going to be the direction of B minus A phi n, which is nothing but Rn. That means I now modify this thing as phi n plus 1 equals phi n plus alpha n Rn. We know that the local residual direction is nothing but B minus A phi n. That is the direction in which we should go by this much amount alpha n. Okay, then that is what we should do. But then, of course, I still don't know how much step should I take. I can somehow calculate what is Rn. So this is the iterative formula that we want to use in the steepest descent method. Okay, let me go back to this one. So we constructed this Q function, which is a function of phi n plus 1. Phi n plus 1 is a vector. Now, how do I calculate a minimum of this thing? I can calculate a minimum of this thing if I can differentiate this with respect to phi and then set it to equal to 0. Okay, so that is what I'm going to do. I'm going to differentiate this with respect to, but then what I don't know is I want to differentiate this. I want to calculate what is alpha, how much amount should I actually, should I take. So I'm going to set this equal to Q dq of phi n plus 1 divided by d alpha n equal to 0. Okay, so I want to take how much step should I take. I'm going to basically differentiate this with respect to alpha n and set it equal to 0. That's going to give me, if I set it to this equal to 0, so dq of phi of n plus 1 by d alpha n is going to be dq of phi n plus 1 divided by d phi of n plus 1 times, okay, so these are all vectors, so I would do a transpose, and then d phi of n plus 1 by d alpha n equal to 0. Okay, so if I can set this equal to 0, I know what is the amount I should take to basically make it minimum. Okay, I know already the direction, but what would be the amount I should actually do it? Okay, we already know what is dq phi n plus 1 by d phi n plus 1. This is nothing but phi prime n plus 1. We have written this thing as a times phi minus b. This is a phi minus b transpose times what is d phi n plus 1 by d alpha n. This is d phi n plus, this is phi n plus 1 equals phi n plus alpha n Rn. So d phi n plus 1 by d alpha n is nothing but phi n is going to be 0. This is going to be simply Rn. That is what kind of remains. So this is going to be Rn equal to 0. Okay. But then what is a phi minus b? A phi minus b or b minus phi a, b minus a phi is the residual at the n plus 1th iteration. So I can write this as minus residual n plus 1 transpose times residual at n equal to 0. So basically that is telling me that if you can take your residuals or your directions such that the next direction is perpendicular to the current direction, right? Only then Rn transpose, Rn plus 1 transpose times Rn equal to 0. That means this direction is perpendicular to the Rn. That means if you take a step like this, so next time, once you stop, you take a step like that. Okay, next time it should be perpendicular to this thing. Okay, take a step like this, and so on, right? It should always be perpendicular. That's what this condition tells, right? Because my Rn now indicates the direction. So this is direction at n, and Rn plus 1 is the direction at n plus 1. That means my next direction should be perpendicular to the current direction. That's what it tells me. Okay. Notwithstanding this minus r, which I can send it to the right hand side, I can write this as Rn plus 1 transpose times Rn equal to 0. Okay. So that's what we have. I want to actually calculate what is the how much step size that we can take. That means I want to calculate what is alpha n. So for that, I'm going to again substitute this back. What is Rn? Rn is b minus a phi n plus 1. So I'm going to take this as b minus a phi n plus 1 transpose times Rn equal to 0. Okay. And I can substitute for b minus a, and then for phi n plus 1, I can substitute this as phi n plus alpha n Rn. Okay, transpose times Rn equal to 0. Okay, so this is going to give me b minus a phi n transpose minus a times alpha n Rn transpose times Rn equal to 0. So I have just clubbed these two here. Okay. Oh, sorry, b minus a phi n times transpose times Rn. So I should multiply this with both the terms, both this term and the second term. Okay, what is b minus a phi n? B minus a phi n is nothing but Rn. So we have Rn transpose times Rn minus alpha n is a scalar, so it can be taken out, alpha n. What is this quantity? This quantity is nothing but Rn. So a times Rn transpose, that is AB transpose, or A phi or A X transpose is nothing but X transpose A transpose. So this is Rn transpose A transpose, and then we have Rn outside is equal to 0. Okay, that means I can write this as Rn transpose Rn minus alpha n. This is Rn transpose. A transpose is equal to A because this is a symmetric matrix, and equal to 0. If I send it to other side, this will become minus, will become plus. So I want to calculate what is alpha n. So what is the amount by which I should take a step in a particular direction Rn? That is going to be alpha n equals Rn transpose Rn divided by this quantity, that is Rn transpose A times Rn. Okay, so this is the alpha n. This is the step length we want to take in direction Rn. That's all. That means we have now the step length, and then Rn is there. That means I can have my algorithm. My algorithm is simply phi n plus 1 equals phi n plus alpha n Rn. So this is the same algorithm. So let us start with some guess value. So we say we initialize, let us say, so the steepest descent algorithm is nothing but I initialize my I take some B0 guess value, okay, some B0 guess, no, not B0, X0 guess value. B0 is given, right? B is given. So I'll take some X0 or phi 0 guess value, B0 guess value, and then calculate what is R0. R0 is B minus A phi 0. Okay. Once I have this thing, that means I am calculating what is Rn equals B times A phi n, right? That is what I'm calculating. Once I know Rn, the residual, I can calculate. That means residual is already telling me go in this direction, right? But then how much should I go? That is given by alpha n. So alpha n equals Rn transpose Rn divided by Rn transpose A times Rn. Okay, so I know the amount by which I should go. Then simply I calculate what is phi n plus 1 equals phi n plus alpha n times Rm. Okay, so once I know this thing, I will say that my new phi n equals phi n plus 1. Okay, and then I go to step 1. Okay, that means I go here and then I perform this, keep iterating until convergence. Okay, iterate till convergence. Okay, then it will converge and then we get a solution in which essentially if phi n is and phi n minus 1 are less than some tolerance up to some norm, then we say that we have converged. Okay, so that is the beautiful steepest descent algorithm, which is very nice. Okay, so any questions so far?
So we will review and we'll get back to you, sir.
Okay, you review and get back. I think this requires some review because this is somewhat different from what we learned in the previous classes. Little bit of algebra and matrix linear algebra here. Okay, so I just want to solve a simple problem so that you get the hang of it. So I'll apply it to solve, let us say, solve some problem solving. Let me take an example, very simple example. 2x plus y equals 11. Okay, sorry, 2x plus y equals 7. And then I have x plus 3y equals 11. Okay, so we want to solve for this 2 by 2 system using steepest descent. Of course, you don't need to apply steepest descent for this thing, but to make hand calculation easy, I'm just applying how steepest method kind of works for this one. But the same algorithm, what we should keep in mind is that the same algorithm can be applied for n size matrix, right? N equations. So which the steepest descent can scale, whereas your regular thing will not, hand calculation will not be able to easily do it. Okay, fine. So how do I do this thing? So my matrix is 2, 1, 1, 3. Okay, so this is symmetric because I have ones on the diagonals here. So and then I have x, y equals 7 and 11. Okay, so this is my A, this is my B. What is the first step? I start with the guess value. So I guess my xy equal to, let us guess 0, 0. Okay, then what is my residual? My residual equals B minus AX. B is 7, 11 minus A is 2, 1, 1, 3 times 0, 0. So my residual is 7, 11. Okay, so that is my residual 0. Okay, residual 0. Then what is my step? My step is alpha n equals R0 transpose R0 divided by R0 transpose A R0. Okay, so what is R0 transpose R0? That is 711 times 711 multiplied by 711, and then we have 2113 and then 711. Okay, so R0 not R0 transpose. So this is 711. Okay, what is 7 times 11? 7 times 11, this is 7 square, 49 plus 121 divided by 711 like this. And then what we have is 14 plus 11, that is 25. Then I have 7 plus 33, that is 40. Okay, so this is going to give me 170 in the numerator. Denominator is going to be 25 times 7 plus 440. Okay, so that is my alpha n. That is the step. Let me just get my calculator. Okay, so what I have is 440 plus 29 times 7, that is 615. 170 divided by 615 is approximately 0.276. So this is the step I should take in that direction. So I know the direction. That means what is my next phi 1? That means my xy 1 values is equal to xy at 0 plus alpha n times Rn. Right? Xy at 0 was 0. Alpha n is 0.276 times residual was 7 and 11, right? That's what we started off with, 7, 11, because that was equal to B. So this is nothing but 0.276 times 7, that is equal to 1.932. And then 0.276 times 11, that is going to be 3.036. Okay. So I have actually just done one iteration, okay, one iteration. But you could do more iterations, but we realized that we don't actually have to do it because the exact solution to this problem is 2, 3. And we are already pretty close to 2, 3 in just one iteration. Okay, this is not a great problem to be solved with steepest descent, but to tell you how we are approaching how we are applying the algorithm we have derived today to this problem. Okay, so that is what I have done to perform iteration. But then, of course, if you perform one more iteration or two more iterations, you end up getting exactly 2, 3 or very close to 2, 3. Maybe you'll get 1.9998 or something, and then 3.002 or something like that. Okay, so you can perform a few more iterations, and then we will get the final answer to within some tolerance. Okay, but what you see here is that in the algorithm there are actually two matrix vector multiplications. Okay, so one is in the calculation of residual, there is one matrix vector multiplication, and there is one in the calculation of the step length, that is alpha n. Okay, A times Rn, that is also there. Fine. So there are two matrix vector multiplications which we need to perform. Fine. I think yeah. So that is the case. Okay, I'll just take maybe a few more minutes and just show you a small MATLAB code I have written for the same problem. Okay, I think that way you'll be able to also present something else. Allow to share screen. Okay. Screen. Okay, do you see my MATLAB code?
Yes, sir. Yeah.
Is the font okay, or should I increase it?
It should be okay, sir.
Okay, fine. So what I have is I have CLC clear to clear the value. So I have n equals 5. This is the number of size of the matrix is 5. I'm initializing my matrix as zeros, n by n matrix as zeros. Then I have B, the right hand side, I initialize it to be ones. Okay, but I'll change this thing. And then X, AX equal to B, X equal to zeros. And then R is my residual, which is equal to zeros of size n by 1. And then I am performing some 10 iterations. And then this is the A matrix. I have given some 5 by 5 matrix whose rows are 6, 0, minus 1, 0, minus 1, 0, 6, 1, 1, minus 1, minus 1, 1, 6, 0, 0, and then 0, 1, 0, 4, minus 1, minus 1, minus 1, 0, minus 1, 6. Okay, this is the 5 by 5 matrix, and we know that this is actually a symmetric positive definite matrix. Okay, this needs to be ensured for steepest descent method to work. Okay, otherwise it's not going to work. Fine. So A is then, B is also I have taken. B is 7, 9, 27, 23, 1. And then I put a quote here because it is a column vector. Okay. So that's what I have done. Then I don't have to do any of these things. Okay. Then my steepest descent method is actually for iterations. I perform iteration equals 1 to n max. I'm calculating what is the residual. R equals B minus A times X. So I'm here heavily using the matrix linear algebra that is used in MATLAB. So I don't have a matrix multiplication, matrix vector multiplication. I'm not writing my own subroutines or functions. I'm just using A star X because MATLAB will automatically calculate it. And then I'm calculating numerator. Numerator is R transpose times R. Denominator is R transpose times A times R. Then my alpha equals numerator by denominator. Okay. And then my xn equals xn plus alpha times R. Okay. And then when I go to the next iteration, I copy my x new to be equal to x old. Okay. X old is now the new xn is now the x old. Okay. And then I display what is the sum of the R just to see how the residual is decreasing or increasing. And then at the end, I'm going to just display what is the solution obtained, what is the A times X. Okay. A times X actually should match with my B I have given, right? Which is basically that 7, 9 something. Okay, once it matches with it, I know that I have done enough iterations. Okay, so I have given some 10 iterations. Okay, so let me try running this problem. So I run this thing, so I get something here. Maximize. Okay, I think now you can clearly see. Okay, so so it is printing the residuals starting with 67. It came down to 4, 8, it's oscillating a little bit, and then it came down to 0.0025. Then it gave me x equals 2.23 minus 0.08, 4.88, 6 and 1.5, and then this is printing, this is the a times x. Okay, a times x, you can see this is equal to 6.99, which is equal to 7, 8.99, that is equal to 9, 27, 23, 1, which is basically the same as what we have given before. Okay, okay, where did it go? I think it went somewhere. Okay, anyway, so my b a times x is came out to be, let me run it again, it may come back. Oops, okay, it has gone somewhere. Fine, maybe I have to view what would that this thing be? What would be the window? View the output window, right? Okay, I think seem to have lost it. I have to figure out how to show that. Anyway, that is fine. I mean, you got the idea. So we were able to get the answer. Okay. Let me see if I have. No, I want to keep it. Okay, I'm able to get that thing. Warnings. Okay, this is okay. Fine. I think hopefully you got an idea of what I wanted to do. Okay, so it is giving me correct answer. I can of course increase the number of iterations and then play with it. It's going to give me even, or if I can decrease and then also see. Okay. Tooltip, there. Command window. Okay, I don't know where it has gone. Anyway, that's fine. Okay, are you able to see the method and everything? Yeah. Hello?
Yes, sir. Yeah. One question is like, can you please explain like what is the solution like refers to, like in general, like does it refers to the equilibrium state?
Which one? Which one?
The solution that we are getting at the end, the x
Yeah,
values
that
or
is the solution to Ax equal to B.
of the physical interpretation, sir. Like, does it refers to the means equilibrium state?
Yeah, so physically, so essentially you want to solve for Ax equal to B. That means x equal to A inverse B is what you want to solve. But then imagine that you have constructed a new function Q, which is some kind of a paraboloid. Okay, I'm drawing a parabola here or something. But then this Q that you have constructed, it doesn't, I mean, it is not part of the problem. That is something you have constructed, which is a nonlinear problem of your linear problem. And the minimum location of that, where Q is minimum, that value where it is minimum, that x location is the same as this x location if you were to solve Ax equal to B. That is the idea.
Okay. Okay, sir.
Yeah.
Okay, sure.
Yeah. So that means instead of solving for linear system Ax equal to B, what you are posing it as you are posing it as an optimization problem. You're saying if I can optimize this quadratic equation, if I can minimize this quadratic equation, the x which minimizes this quadratic equation is the solution to Ax equal to B.
Okay, okay, sure, sir. Like, what would be the advantage of this method compared to the normal method?
No, the thing is, okay, this method is not super. I mean, the thing is that you can get in few iterations, you can get the solution for even for big systems, right? It will be much faster than your Gaussian elimination, not Gaussian elimination, much faster than your Gauss-Seidel, Jacobi, and other things. Gaussian elimination is anyway a direct method, so we are not looking at that method actually.
Okay, sir. Okay, sure.
Yeah.
So,
Yeah,
thank you, sir.
and this is very much used. I mean, if time permits, we'll look at the steepest we have seen. We'll look at the conjugate gradient, which is even more faster than this steepest descent. Okay, with which you can actually converge in just in n iterations. Okay, just in n iterations. That means if you have a system A which is of size n by n, you can simply converge in n iterations. In Jacobi and Gauss-Seidel, you cannot converge in n iterations. You would take much more than n iterations actually.
Okay, sir. Sure.
Yeah,
Sure.
yeah.
Thank
So
you, sir.
these are very much used. The conjugate gradient methods are very much used.
Sure, sir.
Yeah. I think hopefully all of you are able to appreciate this. Okay, so I am going to stop here unless you have any questions. So I graded your midterm papers. They will soon send you your answer, your scores, and if you want, they should be able to even send you the papers. I have them. I mean, I gave it to them, so I don't know whether they'll be able to email them to you or not. I think most of you have performed very well. I think the average is more than 25 out of 30. So all of you have got, like, many people got 30, some people got 28, 29, 24, like that. But on an average, it is very high average. Okay, so I think all of you are able to solve it, without much doubts or anything like that. I guess you didn't have any questions or anything like that. I think there was sufficient time, as you said, and the question paper was also kind of straightforward and easy. Fine. So I'm going to stop here. We will meet on Monday and then continue our lecture. We have to look at the conjugate gradient method. I'll see if we want to look at that. Most likely we will look at that, and then we will look at the solution to parabolic equations. Okay, so these two are remaining. We'll try to finish it up next week. Okay, guys, I'm going to stop here and talk to you on Monday at 4 o'clock.
Thank you, sir.
All right. Thank you. Thank you.
Thank you, sir.
Thank you. Bye. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, Professor, sir.
Thank you.